joining and for your interest in the D2MS2 talk series. My name is Suparna Bhattacharya, and I'm an assistant professor in the Department of Mechanical Engineering at IIT ISM Dhanbad. I'm organizing this series in collaboration with my colleague, Professor Antari Poddar. Um, Professor Poddar, would you briefly turn on the video?
Am I visible?
Yes, you are.
Hi, it is a privilege to be a part of this online talk series. And in this series, we welcome different distinguished speakers who work on data-driven modeling. And then the idea is to nurture a collaborative environment and to expose the students to the cutting-edge research that is going on in this field. Over to you, Super.
Thank you. Today, it is my honor to introduce you to our speaker, Professor Ashesh Chattopadhyay. Ashesh is an Alfred P. Sloan Fellow and Assistant Professor in the Department of Applied Mathematics at the University of California, Santa Cruz. His interests lie at the intersection of theoretical deep learning, dynamical systems, and computational physics. Ashish started his career not far away from here as a BTech in the Mechanical Engineering Department from IIT Patna, and then later moved on to complete his PhD from Rice University, Houston. He spent a year at Xerox PARC, Palo Alto Research Center, and then at SRI as a staff research scientist before moving to UCSC. Today, he's going to talk about some theory, theorems, and scaling in AI for science. Quick guidelines for the audience. If possible, please keep the questions for the Q&A session at the end. However, feel free to use the chat for questions on the go. Okay, off to you, Ashish.
Thank you. Actually, it is fine if it's not a problem with the organizer. It's fine if you want to interrupt me and ask questions. Actually, that is fine by me.
Okay.
So thank you. But I can't see the chat, so if there is a question, please let me know. So this work was done in bits and parts with a group of folks spread across academia and industry. I would like to highlight the PhD students who contributed to this work, or at least some parts of this work. Hyven gone at Penn State, who worked with Romit and collaborated with me, and then Conrad Ainsley, who is a PhD student in my group. There are other people involved, obviously, as I've pointed out here. Troy Arcomano at the Allen Institute for Artificial Intelligence in Seattle, Chiang Sun at the University of Chicago, Pedram Hassanzadeh at the University of Chicago, and Michael Mahoney at UC Berkeley. So the title of this is Theory, Theorems, of Scaling in AI for Science, and I try to clarify what I mean by these, because they come in different flavors, and especially when you cut across communities or disciplines, as you often typically do with data-driven simulation sciences, it's sort of important what we mean by AI for science. So the kind of science problems, the kind of hard science problems that we're looking at in our group and possibly a lot of other groups, both in academia and industry, are nonlinear problems that involve multi-scale dynamics. So these are problems where you have multiple scales interacting with each other, and more importantly, there are interscale interactions which are nonlinear. This is even more difficult in the presence of sensitivity to initial conditions that we call chaos. And a typical example of such problems are in generally fall under the broad umbrella of turbulence. And turbulence is one of those possibly last classical unsolved problems in physics or classical physics. And applications of turbulent flows, or understanding, controlling, predicting turbulent flow, is important in a variety of different engineering applications, whether it's in process industry, aerospace, and also in more natural sciences like weather, climate, and atmospheric dynamics. So I specifically focus on problems that deal with maybe aerodynamics, So that would be falling under engineering flows, or whether climate and atmospheric dynamics. That's more of my specialization in terms of the applications that I focus on. So those are the kind of hard science problems that would be looking at. Now, obviously, there are other applications or other application areas that AI has generally excelled at. For one of the prominent ones being in molecular biology, where protein simulations, general molecular simulations have been accelerated with AI. And now that's also a multi-scale nonlinear problem, but in many ways are different from the kinds of problems that we're interested in turbulence. And while this is kind of beyond the scope of how they're different, they share some similarities. Some of the ideas do translate there. Many of the ideas don't at the same time. Now, and now this is a bit of a preamble and perhaps more important than just a set of results. Uh, One of the things that we're very used to doing when we're building models, we're building data-driven models or AI models for any kind of engineering application. The approach that we take to building these models is very different from the approaches that we have taken over the years to build numerical or physics-based models of these systems. And physics-based models have always come from a perspective of reductionist sciences, where we usually have a hypothesis and we build a theory around that hypothesis, and then we build models. While the way we have done data-driven modeling has been, we started with the model and then sort of try to see or try to look at regimes where this model breaks, and then confine that model to a regime where it works. So which is very atypical of how scientific modeling work over the years have been developed. And an example of this is that when you're building a bridge, um, probably this is a nice analogy, not quite an example, that when you're building a bridge, neither do you start from a hydrogen atom. You don't do quantum simulations from a hydrogen atom to build a bridge. At the same time, you don't start by building a bridge, then running a tank over it and seeing whether it breaks or not. You have something in between. You have physics-based equations that you trust, that are reliable, but at the same time, something that is sort of automated on a spreadsheet, in the sense that you have design principles that you follow and you trust it because they're reliable, and you build a bridge out of it. You don't start with either of the extremes. Machine learning has either been, let's start from theory that first defines the distribution of data and then leads you nowhere, or it's been about, let's build a big model, see where it works and see where it doesn't. So we have this large vacuum in between, where we don't see trustworthy theory, or the kind of scientific theory that we're used to. And a scientific theory is very simple. It's, you see the world, you observe the world, and you posit something. So that's your hypothesis, and you make a prediction with this hypothesis, and then you see whether this prediction is right or wrong. So this positing something based on the observation is built on a priori principles or first principles that you believe in. More importantly, the great thing about most scientific theories are that they're falsifiable, which means that you can prove it to be right or wrong. Unlike many of the theories that is very prominent in theoretical computer science, for example, VC theory, where you can't say whether it's right or wrong, because in most cases you cannot actually compute the things that you need to compute to be able to falsify this theory. And falsify basically means, with an experiment I can say whether something is right or wrong. Like for example, if I assume a theorem which is F equals ma, a very data-driven theorem, and then I have a system, and I measure mass and I measure acceleration and measure force, and I can posit whether F equals ma is true in this particular system or not. VC theory, which has been the kind of theory popular in machine learning, has not been able to do that. So it leads us to generate vacuous bounds and so on. So when we want to build theory for scientific machine learning, the kind of applications of AI in science, we want to build theory that is very similar to a practical scientific theory that we're used to. And the kind of theorems that I would talk about would really not look like theorems, because again, the way theorems have evolved in this field is, like, for example, a theorem on stochastic gradient descent is a theorem where under certain assumptions you show that the gradient descent algorithm converges with sort of strong assumptions. Now that's a great theorem, except it's not very useful. It often gives us vacuous bounds, which means bounds that we can't actually compute. But the way we are thinking about theorems is similar in principle to a thermodynamic chart, which is, if I want to design a model, or the example of building a bridge that's similar to a didactic, where if I want to build a model, if I want to design a model, different parameter regimes, what are the principles that I should follow? Something like a phase diagram. So that's the kind of theorem that we're looking for, or a theorem that tells us, given a model, whether this would be stable or accurate, or whether two models that we're given and we can't really chew more on that model, can we say by looking at certain things in this model, certain properties of this model, whether this would lead to a better approximation of the system that you're interested in, or some other model would be a better approximation to the system that you're interested in. So that's the way we're thinking about theory and theorems in this particular system. Now, the kind of problems that we're interested in this nonlinear setting is, say, a problem where generally you don't know much about the system. Maybe you have some rough idea about the governing dynamics, but you have some time series data corresponding to it. So you may have some sparse time series data, you may have very clean high resolution, or some noisy time series data, and you want to build a model that can do the following. Maybe you're interested in aerodynamic modeling, and you work for an automotive industry. So think about a problem where you want to be able to predict lift and drag, and you don't want to predict lift and drag by running long CFD simulations with different geometries, but rather you want a model that directly gives you this value. So that's one of the kind of the problems that are pretty popular. There could be something a little more a little less direct and a little more fundamental, where you're trying to predict the state of the system at the next time step, given a historical observations of the state of the system until today. And this is typical in an application like weather prediction, but also applications in other things like combustion design, where you're trying to combustor design, where you're trying to predict the evolution of pressure waves and so on. But this is sort of more fundamental, because this is similar in principle to what a PDE solver does. It integrates equations based on the physics to be able to give you a full representation of the state of the system in future time steps. Doing this with sort of machine learning models are very lucrative, because the key element here is that running these models are orders of magnitude faster, and there's no comparison between how fast a machine learning model is once you've trained it on data. So obviously there are some practical advantages to having this model. Now, the kind that I would be talking about is very similar to the second one, but actually goes beyond prediction, where you set up the problem in a very similar way. You set up the problem like a PDE solver, where you're trying to predict the full state of the system given a historical time series, and the time series can be sparse, can be noisy, and whatever. But the idea is that you're not just predicting a few time steps into the future, or the next state into the future, but rather you want to use this model to be able to emulate sort of emergent dynamics, which means that despite the fact that you have trained it on a few time steps, you want to be able to unroll it for thousands and thousands of time steps into the future, so that dynamics that are emergent in the system, dynamics that can only be observed after very long rollout, it can be simulated in a very efficient way. And an example is a climate model, that if you are able to run a weather model for a long period of time, sort of the emergent phenomena that comes out of it are persistent patterns that we call climate patterns, or things like molecular simulations, where you get a stable structure that is emergent from Newton's laws with a potential function that you've defined for the interatomic interactions, or things like statistical mechanics. So that's generally the idea. And the questions that we want to ask is that, what does G need? Does it need physical constraints? Does it need sort of the same ensemble of techniques that we have learned in numerical methods? Do we have to embed the equations inside to be able to simulate this properly? Do I need to build architectures that are custom for certain scientific applications? And all of these are bad requirements. Bad in the sense that in most cases you don't know what the physical equations are. Stability is in a different beast altogether. If it's a nonlinear system, there's no such thing as stability per se. And choosing architectures that closely mimic dynamics is just like doing research on architectures every time you have a new problem. So if you actually need this, that's not a great sign for AI-based modeling, but in some cases you might need to. Now, there's one aspect of it is building good models that can actually do the third problem. But also beyond that, what we need is a good theory of these models, which means to say that based on whether or not I have a great model, or an intermediate sort of quality model or a really bad model. I should have theory that tells me about the quality of these models, that tells me about its limitations, that tells me about its potentials. Um, and more importantly, that theory should scale. It should scale in a way that is agnostic to whether it's a transformer or a UNet or any of the other 100,000 different architectures that are out there. It should be agnostic to the equations of the system, because in most cases you don't know the equations to the system. Um, so these are some of the requirements that a great theory has, right? So F equals ma is independent of the actual system that you're concerned with, right? It works for fluids, it works for baseballs, it works for planets. It doesn't work for very small particles after a specific wavelength, but that's a different story. In most cases, like a good theory generalizes to any sort of scales, any sort of time scales or spatial scales. So that's the kind of theory that we're thinking about. Now I'm going to jump right into an application where we build models that look like this, that look like the second one, like weather prediction models, and then think about, okay, like what are the properties in this particular model, and how can we build theory around it. So the first example is that of ForecastNet. ForecastNet was a big collaboration between us, NVIDIA, and a few other folks, where we took a very large AI model, and it's not really important throughout the length of the talk. It's not really important what that AI model is. It's just one big large model with many parameters. This was a few years back, so 80 million parameters, 100 million parameters was a big model. And the way we trained this model was we looked at historical weather states or historical states of the atmosphere, and asked the model to predict the next state. So the way this model was trained, it was shown the states of the atmosphere at time t, and the labels corresponding to these inputs were the states at the next time step. And then this model was completely agnostic to all the equations that are there in a particular weather model. Now, that doesn't mean that we don't know what the equations are in a weather model, but they're obviously not the complete set of equations, and there are biases in those equations. So really, the objective of this work was to see how much can we scale an AI model without constraining it to the physics of the system that we already know about. And the results were very encouraging. First of all, these were extremely fast models, so they're 100,000 times faster than the sort of the gold standard of weather prediction. And this was sort of trained on a whole bunch of it was trained on the entire 3D atmosphere, so it was a very operationally useful model, which means that it's not a toy system. It's not something that you build. It's not a method that you showcase in a research paper just for the sake of it. It was really meant for operational forecasting. So it's a plug and play model that you take, and you can do at scale weather prediction at 25 kilometers, which is the highest resolution at which you can do global weather prediction. The results that we got were very encouraging. Firstly, the thing that was very encouraging was the fact that we were able to outperform the gold standard numerical models. Now, this particular bit might be a little confusing for people who are doing engineering, where it's very common for folks to train models on simulation data. So the best that you can do with your model is what your simulation provided. Like if you train models on CFD simulations, you can't outperform a CFD simulation. This is a little different. This is where you have trained models on observational data, real satellite-based observational data. So there is a good potential for your AI models to outperform the best physics-based models, especially at scale, where there are 100 different ad hoc approximations in these sort of operational scale models. So this was something that we saw in action, that we were able to outperform these AI. We were able to outperform the gold standard physics-based models, and it was very encouraging because this told us, it sort of reinforced a story that we have heard for a very long time, that if you want to get AI to work, you need to scale it. You don't need to teach domain physics. That's a bit silly. Almost all success stories, and to be honest, apart from weather prediction, protein structure prediction is the only other truly operational success story that we have in AI for science. But in both the cases, the magic sauce was not in the constraints of the equations. It was really about the scale. It's trained on a lot of data, train a very large model, and if you know how to train these models, then you would be able to get the performance that you're looking for. And this was reinforcement not just from these folks at NVIDIA and us, but later on, it was Y and DeepMind who released these models and showed that, again and again, you can get AI models that outperform the best physics-based models for problems where you have real experimental or observational data, which is of a better quality than the best simulations out there. Today, the leading European Center for Weather Prediction that gives us state-of-the-art models actually run operational AI models for their weather forecasting, which is now sort of documented to be a better model than the physics-based models. So this is very encouraging results, but of course, there's a catch. There's a catch to it. And the question that we started to ask was after the forecast net paper is that all these models, they're trained with the same principle. And this is not just about weather and climate. This is about any engineering problem where you're trying to build prediction systems or emulators, which is a very common sort of application that you see in the sciences. And you're trying to discretize a PDE into a set of ordinary differential equations, and you're trying to approximate the right-hand side of this numerical integration with a large neural network. So, the common ends that you see out there are neural operators like Fourier neural operators or depot nets and all these kinds, and they're all solving the same problem. Some of them are doing it on toy problems, some of them are doing it operationally, but this is pretty much how it's set up. And there's a loss function that minimizes the difference between what it predicts and what it predicts and what is the true state at the next time step or the next few time steps. And the question that always pops up is that, okay, every time make a small change in your n, and you get 0.1% better accuracy, but there is no great understanding as to why that happens. When you don't get that change, when you don't get that improved accuracy, we often resort to saying that our data is unique. For the longest time, at least during my PhD years, we used to say that turbulence is unique because it's the most difficult problem of all. So you can't possibly have AI models or data-driven models that can represent turbulent states in an evolving flow. But clearly that's not the case. So neither is your data unique, nor is there a magic sauce in your architecture. So something else is going on there. The other problem which is less philosophical and more practical is that usually we see that models that are trained to predict longer time steps do better than models that are trained to predict smaller time steps because of error accumulation. And while it makes a lot of sense in the context of AI, this is really hurtful to a numerical analyst, who have developed theory over the years, saying that smaller delta t usually yields a better model, and higher resolution is always better. So this kind of doesn't make sense, and the reason why this happens needs to be better understood. So what we first started doing was we took one of these large N models, or rather all of these large N models in the domain of weather prediction, and we started unrolling it into the future for longer time steps. Instead of looking at predictions at 5 days or 7 days or 10 days or 15 days, we started unrolling it and see what is the emergent dynamics that comes out of this. So for example, we took our model just so that we're not being biased to everyone else. Our model rolled out for 30 days, which is about 120 time steps, 4 time steps per day. This model becomes unstable, and that's interesting because this model at the day or the second day or the third day or up to 10 days were giving you predictions that were better than the physics-based models as compared to real observations. But when you unroll it for 30 days, it kind of blows up. It wasn't surprising because, well, these models do not know anything about CFL condition. It doesn't understand resolutions and things like that. So that's interesting. And this happened to some of the other sort of state-of-the-art models as well. While there was another class of models where if I unroll them, they actually had some emergent dynamics. And in fact, if you're not a climate scientist, you look at these models' predictions, and then I'm looking at pressure maps over the Earth's surface, and it kind of looks right. So like high pressure is high temperature. That's how you can think about it. So the Arctics are cold, the tropics are warm. This looks like the Earth. So I'd be inclined to feel that this is getting you the right emergent dynamics at long time scales. But then when you actually go and look at the statistics generated by these models, so the way you interpret these plots are that the black line is the observed truth of the Earth system, and all the other colored lines are all the other state-of-the-art AI models, which, by the way, were outperforming anything that was physics-based out there. But at longer time scales, if I look at averages or invariant measures of the system, I see that they're completely off and very, very different from what you would expect or what you'd see in the observations. And one might be inclined to say, well, you're unrolling a data-driven model for so many days, you don't expect your averages to be, spot on. Maybe they're going to be a little different. Doesn't mean they're wrong, but then they really are, because they get fundamental physics wrong. For example, if I track the blue line, which is one of the frontier lab models from Hawaii, it shows that the equator should have 30 meter or 20 meter per second wind velocities, which would destroy the Earth if a thing like that would happen. So the emergent dynamics is very incorrect in these systems or in these models. And so we wanted to ask fundamental questions as to, okay, let's understand what are the properties of these models that make them behave this way, because we don't have great theory for it, so we need to build good theory for it. So the first thing that we want to do is, can I look at these models alone, or do I have to build structures around these models so that I can predict its behavior? So it's important to take a second look at this question. It's one thing to build structures around your model so that you can make better predictions about the system, so that you can better represent the physics of the system. I'm asking a different question. I want to build structures around these models so that I can make better predictions about this model's behavior, because I could not say beforehand whether any of these models would behave this way or simply go unstable. So I want to build structures that, sure, maybe downstream helps me represent physics better, but first and foremost should be able to tell me about this model's behavior, because we surely do not know how to understand model behavior, something that we absolutely do when it comes to numerical modeling. We know everything that is there to know when we build a numerical solver of a turbulent flow simulation, for example. So the way this is going to go is that we're going to take an approach that is a little different from the reductionist sciences approach, which is theory, observation, hierarchical modeling are tightly coupled together. That's how we do physics. The way we are going to do is, first we will build structures with some intuition that we have always done in machine learning, and then quickly go to hierarchical modeling and see whether this intuition works in practice. From there, we are going to distill a theory out of a theory of these models out of these modeling exercises. This is called semi-empirical analysis. This is also not new in physics. In fact, quantum chemistry is built on semi-empirical analysis. A lot of quantum theory is built on semi-empirical analysis. And then we want to look at this theory and see whether it scales at a real application. In our case, a real application is a full-blown climate model. Can we basically write an AI-driven climate model that walks like a climate model and talks like a climate model? That's sort of the goal of this whole talk. Okay. So what we first do is we see that there is a problem with these models in the form of spectral bias. So the spectral bias is a concept that has existed for a while, but in the sciences, this was brought by us in 2023 in this paper. The models, after a few days of emulation, starts behaving differently in spectral space than they're expected to. So this is the Fourier spectrum of the variable that we are predicting. And one may be inclined to think that, okay, by 10 days, so that's like 100 time steps of prediction, you have accumulated enough error where your spectral energy is going to vary from the ground truth. So again, the black line is the ground truth, which is observation. All the other colors are frontier AI models that, once again, do very well when it comes to a few days of prediction in terms of a few days of weather prediction. And we realize that this is not about error accumulation, really. In fact, it's there at the first time step of prediction. You actually capture only about 1/4 of the wave numbers. So this is something inherent in these models that has nothing to do with how we train them per se, nothing to do with the data on which we train them, but rather something that can be derived from the first principles of how a model's inductive bias is designed. Inductive bias is sort of the architecture that we have in this model, and this is common to all architectures. So you don't get about 3/4 of the wave numbers. So obviously, if you do not get 3/4 of the wave numbers, in spectral space, we know that the whole point of turbulence, the whole sort of unique selling point of turbulence is the fact that all these scales interact with each other in time. So if you don't get them right, you're either going to blow up, where your energy is going to keep on increasing, the way we see in this blue colored model, which is a Pangu model, or you're going to diffuse down and become super saturated and show on physical dynamics that look stable, but in reality is not. Now we can actually track this problem across literature if you look at the right metrics. So basically, we looked at a bunch of different papers, not by us, but by other people, where they kind of find the same problem. And in fact, they find the same problem even if you're training models on like natural images, like classifying cats and dogs through like autoencoder based representations. So it has always been there. For certain problem, it's an actual issue. For certain problem, it's not. Like if you're doing things like flow behind a cylinder, if you're predicting the flow behind a cylinder at low Reynolds number, your flow is so laminar that you don't really need any of the high wave numbers. You can get away with it. But as soon as you crank up the Reynolds number, your model is going to crash. So depending on the, so this is exactly like a thermodynamic chart, where depending on the regime, you are going to see a phase change where the model breaks or you won't. But it really depends on where you're, at which regime or which parameter regime you're running this model. So this is called spectral bias, and the spectral bias can be derived from first principles. So we are first going to derive it and then try to propose a solution to it. And to derive it, we first want to ensure that this is not a one-off thing, that we can isolate this phenomena in a system where all the states are known and so on. So we look at a very simple fluid dynamical simulation, very high Reynolds number fluid dynamical simulation where you have turbulent eddies and so on, but you don't have all the complexities in a weather model. And you see that it follows the physics almost identically, that if you have high wave number mismatch in your system at the first time step of prediction, this is the first time step of prediction, as you move on in time, the inverse cascade in your energy is going to make your large scale structures disintegrate and eventually cause an instability. And the way to derive spectral bias is to take a one layered neural network, look at its activations, and then, okay, so, depending on the audience's background in mathematics, this might be a little, uh, you know, a little intense mathematically, but really what we are doing is we are taking the Fourier transform of basically rewriting the forward equations of a neural net in Fourier space with the tangent hyperbolic functions. Then we're going to compute the loss function in Fourier space, assuming that it's a L2 based loss function. The idea is that we're going to compute the gradients of this loss with the parameters involved in this neural net. So let's say the parameters are W, B, and A. Then we see that the final expression of the loss, of the gradient of the loss in spectral space, scales exponentially with the wave numbers, which basically means, so there are two terms here, AK, an exponential of minus the absolute value of K. The difference between the predicted and the true spectrum is AK. And for a decaying spectrum, which is typical in most engineering or natural systems, this quantity is very small. So the first term is zero. An exponential minus of a large quantity is zero. So it is close to zero. So this quantity becomes very small. So during training, after you have reached a point like this, your gradients do not update itself. The gradients are not updated anymore. So your model stops learning. So you're always left with this bias, no matter what you do. Cranking up the amount of samples do not change it. Changing the architecture doesn't change it. The only way you can change it is by either changing the activations in your model that would essentially mess with this expression, or by changing the loss function in some way or the other. So the way we decided to address this was to first ensure that if we have spectral bias, then we can mitigate how quickly it grows through the scales. And secondly, so that's sort of the first measure. If we can't get rid of spectral bias, let's delay its evolution in time. So the way we are going to do this is with something that we've done for a very long time, which is numerical integration. But this time, instead of writing out a numerical integrator for the physics-based equation, we will assume that we are representing the time derivative with this neural net. So nothing in this model training changes, except we'll have a differentiable layer that implements your favorite time integral. So you can differentiate through H and back propagate. You basically have a system that respects higher order integration. So you have some control over the stability of these models. And the second way we do this is where we have a loss function in spectral space, except this, what the loss function would do is it would only focus on the wave numbers that you're not capturing in the MSE-based loss. So that this extra penalty term is going to force your loss function to look at the values or the energy at the wave numbers which you have not captured with your regular loss function. So we have this two-pronged approach. We plug them together and we run this simulation for 300,000 days. We call this framework the force framework. We see that the long-term statistics is actually going to match. So having these two prongs together does induce stability in the sense that the emergent dynamics starts looking right again. So we look at things like the POD modes of the system. So EOFs are analogous to POD modes of the system, and the emergent dynamics of the system can be captured if you can retain the spectral sort of consistency of the model throughout the entire length of inference. So you can find more about the math and sort of the derivations here in this paper if you're interested. Now, so do I have like 20 minutes, 15 minutes? How much time do I have left?
20 minutes approx.
Okay, great. So so now what? Now this
Actually, sorry, we have 20 minutes, including question and a 10 minutes question and.
Okay,
Yeah.
sounds good. I'll try to.
But it's okay. You continue. It's going great.
Okay, great. Thank you. Yeah, I'll try to wrap this up in 15 minutes. Maybe spend some more time here. Okay. So the kind of thing that we did over here, and I want to take you back to what we actually did. We said that instead of representing this entire right-hand side, so I'm going to put up my laser pointer. So instead of representing this entire right-hand side with a large neural network, let's do something a little more conservative. Let's represent the tendency or the time derivative of the system with a neural net, which is typically what you do in a numerical solver, right? You represent the time derivative as a function of the spatial derivatives. That's how you write the numerical solver. Let's do something similar. Don't change anything about your model. Take that same big giant neural net, but throw it at the derivative. Don't throw it at the state. And then to get the state, write a numerical integrator using this representation of the time derivative. So the way your model training changes is that instead of saying that my loss function is n of xt minus my truth, my loss function now looks like this, which is a few other terms minus xt at the next time step. So it's a small change in your model that does not involve either thinking about what is going on in this large model or interpreting this architecture in any fashion whatsoever. So based on this, we want to understand, okay, despite the fact that we see that the model becomes stable and so on, this is not really an RK4 solver. It just looks like an RK4 solver because I built in structure that is similar to that. The questions we want to ask are, can we build stability theory the same way we can build stability theory for a real RK4 solver, the one that we used in numerical solvers. We have a map and so on and so forth. So again, why are we interested in this? Because many n's are inference time unstable, some of them are not. And the other question is that we have this issue where large delta t made these models perform better than small delta t, which really doesn't make any sense. So we want to build a general theory that determines n's quality, stability, and sort of other things that we're interested in. Now, such a theory, and again, this is a bit of a preamble without showing you a lot of math, but the philosophy of this theory should be such that you should not, the goal of this theory is as follows. You don't need to say anything about this model. You don't need to judge the quality of this model by running many evaluations. You should be able to diagnose a few parameters from this model, and more importantly, during training time, that tells you how it behaves at inference time. So we should know how a model behaves at inference time without actually running inference. If you are able to run inference, then you don't need a theory, just do what you observe, right? So that's the main motivation. And as you can guess, such a theory basically means you need to understand how error propagates through these models, exactly the way we know exactly how to quantify how error propagates through an RK4 solver in any CFD simulation. Obviously, it would look different in the case of machine learning models because you don't have equations there, but that's generally the kind of theory that we're aiming for. Finally, this theory should scale. It should scale to different systems, flop constrained experiments, all sort of neural scaling stuff that you do. And this again you can find in this paper where I'll show you some of the key elements of this theory. But the idea is that I need to build a stability theory that is analogous to physics-based stability theory, and something that lets me gauge the quality of models without running inferences or thousands of inferences. And the way we are going to do this is we're going to follow a numerical analysis textbook for the longest time until we hit a block. We'll come at a point where we can't do, we'll arrive at a point where we can't do any more math. And you'll see where that is. So, assume that the true system is G, the neural network is G tilde. The error is given by GUT minus GUP, right? You can't really do any more analysis after this because you don't know what is the structure, because this is a big transformer model. Who knows how to deal with it? But the first thing you can actually do is you can linearize the system with respect to UT and then get an error term at any time t, which is a combination of these two. Now, here's where things start to get interesting. You now have your error, which is a combination of two different types of errors. One is the generalization error. This is basically what a machine learning paper reports as the quality of a model. You do training, then you test on a bunch of unseen initial conditions, and you report the testing error. That's a one time step generalization error. But then you have a second term that you typically don't see in any ML model training, which is the Jacobian based amplification. And this is unique to a dynamical system, that when you're trying to model dynamical systems with machine learning models, of course, the Jacobian amplification term will come in. On the other hand, if you're a physicist who have done dynamical systems forever, you know what this is. This is the linear stability matrix. If you're doing linear approximation of a nonlinear system, this is how your error grows. So depending on which community you come from, you have either seen this and not this, or you have seen this and not that. Basically, in this system, both of them are interacting with each other. Now, if you want to do an n-step autoregressive rollout, this expression just becomes nasty and you can't really chew on it. But for a while, if I just focus on this Jacobian amplification, I can get a sense of stability just by looking at this Jacobian. So let's take a look at the example. Let's take a model that directly predicts the state of the system. The Jacobian of this model is a giant matrix, a giant square matrix, where the eigenvalues of this Jacobian determine your local stability, and you have no control over it. You train the model, you hope for the best. However, if you train a model with this integration-based constraint, where you have an RK4 sort of integrator, you automatically or sort of implicitly induce stability into these models. How do you do that? If I take the Jacobian, its identity plus this term, if delta t is small enough, then these eigenvalues are all going to be clustered at 1. And you run an experiment, you see this is exactly what you see. The error in one model blows up because these Jacobians have unbounded eigenvalues, basically eigenvalues greater than 1, while this Jacobian has an eigenvalue that is clustered at 1. And interestingly, this is a 1,000-dimensional system. It's not important what the system is. There are 1,000 eigenvalues that are clustered at 1 because basically this matrix contributes very little owing to a small delta t. And you have a very small error growth corresponding to this neutrally stable model or almost neutrally stable model. So this is why having an integration constraint induces stability, not because it looked like an RK4 solver, but because the Jacobian structure, which is involved in your sort of error amplification, now has identity as one of the matrices in this decomposition. So it has eigenvalues equal to 1 that makes it neutrally stable. So what we did next was something akin to what neural scaling people do, is we looked at, and this plot is a lot to parse, so I'm just going to tell you what the story is. We looked at 40 different models, different architectures, different loss function, different methods of training, we have classified them into two categories, one without integration constraints, one with integration constraints. So two of them are without integration constraints, and then 38 of them are with. All of them have roughly the same error growth, and they have the same error growth because all their eigenvalues are basically clustered at once. So they're clustered at this point, and if I zoom that point in, you see their numbers are basically 0.999 to 1.000 if I cut off 3 digits. So they're basically all clustered at the unit circle. So they're all neutrally stable. Whatever model has a larger eigenvalue has a larger error growth. Whatever has a smaller eigenvalue has a smaller error growth. So this is what a scientific theory looks like. So now we have a thing to go and chew on that tells us how a model is going to behave. And that thing is as simple as calculating the eigenvalues of the Jacobian matrix. And in fact, if we analyze it a little bit more, and you can ignore the math for the time being, what you would find is that the error growth can be determined as a linear scaling with respect to the eigenvalues of the H matrix. This H is basically the identity plus H structure. So if I'm going 3 time steps into the future, it's going to be 3 times the previous error. So a linear scaling law automatically emerges. So again, these are 40 models plotted. On the y-axis, I have error at the next time step, and it scales linearly with the largest eigenvalue. Basically, it means that whatever model has larger eigenvalue would have more error growth, so is more prone to be unstable or not getting the emergent dynamics. Well, anything that has smaller eigenvalue would be a better model in general. And there are some computational reasons why you don't actually have to do an eigenvalue decomposition to calculate them. You can get it from the trace of the Jacobian. Similarly, these eigenvalues diagnose the spectral bias in these models, which is an impossible thing to diagnose otherwise. So essentially, this little theory tells us that these models can be diagnosed in terms of quality just by looking at their Jacobian eigenvalues. We went a step further and we tried to see whether other things about numerical analysis holds true here. For example, we can implement this integration constraint as an implicit integrator, which from numerical analysis we know would lead to more stable eigenvalues, and that indeed holds true here. As soon as you have this structure, a whole wide, rich literature from numerical analysis is translatable to machine learning models as well because of this identity plus structure that comes out. And you can use this structure, obviously, as soon as anything that is diagnostic can be used as a regularization. You can use this structure to have a Jacobian-based loss function that penalizes your linear error growth. So essentially, any model with this Jacobian structure would have lower error growth or lower total error, which means you have generally lower error growth over time or a more stable model. But this is more like a regularization. I think the key point here is that you have a diagnostic to be able to tell which model is going to do better without running inference just by looking at eigenvalues a priori. Finally, this allows us to build a physical model of error propagation. And the long story short of this physical model is that error propagation in these models do not behave the same way as physical models. They're actually a damped oscillator. The impulse force of this oscillator, the forcing, is given by the generalization error. The restoring force in this case is given by the Jacobian, because once you remove identity from there, it becomes a negative trace quantity, and then nonlinear stiffness comes with delta t structured, and then you can keep adding more and more terms as you move on in time, as you increase the value of delta t, so that you get sort of cubic like Duffing oscillators and so on. Basically, these in a general sense, for any value of delta t, this is a spin glass system, a classical icing model that we learned in statistical physics. So your error propagation as a function of delta t would behave regularly as long as your delta t is small, but would behave like spin glasses when your delta t is large and you have these triple products of Jacobians coming into the picture. And we did some scaling experiments, which is a mouthful at this point, to show that indeed these terms can be diagnosed from the training data, and they have this sort of U-shaped structure, which is akin to a nonlinear oscillator. So delta t, like error as a function of delta t, has this U-shaped structure where for large value of delta t, the nonlinear stiffness kicks in, and you have these U-shaped structures and so on. So this is a bit about the theory, and I want to end here, except probably just leave this slide on, that we took this theory and we implemented it at scale for two sets of models called Lucy. These are comprehensive climate models that takes the entire 3D atmosphere state, forcing in terms of CO2, the ocean states, and gives us an emulator for the whole Earth system model, atmosphere only Earth system model, and how it responds to changes in CO2 and so on. And this theory is like implemented for a large model, looked at real data, and it sort of scales seamlessly. So what I do is that I wouldn't have time to go over these results, but you can look at these papers. They're all on archive. This is already published. This is on archive. If you're interested in climate science, we took this theory and we applied it to NSFNO, and it seems to hold up at scale as well. Okay, I'm going to stop here and take questions.
Thank you for such a great talk. Audience, feel free to unmute yourself and ask questions if you want to. You can also use your chat box to ask questions, which can be accessed from the top. So I think there is there, no, that was previous one. Okay. So I do have a couple of questions, but I mean, very insightful. I actually didn't come across this kind of insight before. I mean, I did. So have you, for example, in numerical integration methods like RK4, or if it's implicit or explicit, depending on that, we can decide a stability, as you were talking about, we can decide a stability boundary. And based on that, we can decide our delta t. So, so is it possible to derive any such insight?
Yeah. Yeah, so that was exactly the goal. That was basically the goal. It is not as clean as that of an RK4 stability map, because the way these terms into because in an RK4 stability map you don't have this term. When you're unrolling a physical equation, you don't have this forcing term which comes from machine learning. You just have this Jacobian amplification term. So it's much easier for us to construct that stability map. Once these two start interacting, you have this sum of Jacobian projected onto epsilon, then product of Jacobians projected onto epsilon. So the way the delta t versus error looks like is primarily U-shaped, which means that there's an optimal delta t that you can choose to get the best mean error over a time horizon. And that mean error actually changes with your compute. So basically, as you change the total amount of, so these are called flop constrained or isoflop curves. Each of these delta t's that we have run experiments for have the same total number of floating point operations. And as you keep increasing the flop value, as you allow more and more compute power, the delta t may move to the right or may move to the left, but the total error would go down if you're doing things correctly. So there is an optimal value of delta t, but computing or like a priori diagnosing that optimal value of delta t requires access to the trace of these eigenvalues. So when you're training the model, and you don't want to run it at very large delta t, all you have to do is train a model such that its trace is as negative as you possibly can obtain, because this is a restoring force. This removes the forcing from which increases the error. So the value of delta t that has the largest negativity in your trace would be your optimal delta t in this case. So the stability boundary is not as clean, um, but nevertheless very interesting because it eventually turns out to be very different from that of a traditional numerical solver for large values of delta t. When
Hmm.
delta t is small, you can ignore this, and then you have a very clean case. But
Hmm.
when delta t is large, it's not clean anymore.
Right. Right. Yeah, that makes sense. So currently, do you have any just wanted to clarify one thing. This the underlying assumption is that you are using the neural network to approximate the derivative, which
Correct.
is similar to neural. Is it similar to neural ODs? I mean, that's what
Exactly
I
exactly like neural ODs.
r- right. So in that context, only then we have this idea of delta t because we have to integrate, and then these insights will be the
That,
key.
that is true. So if you do not have that a structure like that, then you're basically uh, so this is a model that doesn't assume anything about g tilde. So your error propagation looks like this. So if g tilde is not identity plus delta t times h, then you basically have no control over these eigenvalues.
Ah,
So you can still track the Jacobian. This is still the term, or well, the first element of this expansion is still the term that will reduce or will act as a restoring function for your error, but you do not have a way to control it. If you have the identity plus structure, then you have a way to control it using this delta t. So if I expand g to be I plus delta t times h, then the identity term comes out with epsilon and gives you this term. And then you can control these eigenvalues just by changing delta t. So neither of these approaches are right or wrong. One of these approaches, my approach, allows you to do this analysis in the sense where you can change a parameter and see how things would move. If you don't have this structure, then you train different models and see how delta g's eigenvalues look like, but you don't have any control over it.
I see. We have a question from the audience. Arpita says, "Hello, sir. Thanks for such a great talk. Just two or three small doubts. One, if we are able to find spectral biases, how much less challenging does it become to emulate a weather model?"
Um, so emulating a weather model for long time scales require you to control spectral bias at every time step. So if you can identify the spectral bias, then you can use a loss function like this. What this loss function, so suppose you have identified what your spectral bias is, which is that the last 10 wave numbers are not captured in your sort of base model. Then you can use a loss function where you have a penalty term that only enforces the last 10 wave numbers, and you fine tune your base model with this penalty term, and then you can mitigate spectral bias at that time step. So that way you can keep emulating the weather model for very long time scales, despite not having a forcing function or a boundary condition and things like that. In reality, this is much harder to do because if you go and sort of read this paper, if you do this experiment on a very clean system like this 2D system, you'd see that at every time step, despite the fact that you have sort of controlled the spectrum, at every time step, even the machine precision error starts to multiply because that's the nature of chaos and turbulence, right? If you have error at 10 power minus 8 and you let it accumulate for enough time, it would start creating problem for you. So in reality, it's much more difficult to contain if you have very high resolution systems where you have a long tail of your wave numbers. That is why the ideal way to do climate simulations is actually with AI models is to actually reduce the resolution at which you're doing the emulation. That way, your spectral bias is much easier to control. Because if the flatter this line is, the lesser there would be spectral bias. High resolution means this is a very long tail, very steep slope.
Mm. Right. The second question is if we avoid biases from ML completely by taking best of both worlds, by using some kind of hybrid setup of ML and NWP.
Mhm. Right. I mean, that's something that, people have been doing for a while, like, data-driven parameterization, and we have also been interested in this. Um, I think there are two things to it. One is the kind of speed up that you get in a full emulator is exponential. The kind of speed up that you get in a hybrid model where you're still solving the primitive equations, but you're only approximating the parameterization, like neural GCM, for example, or those kinds of models. The speed up is obviously less. First of all, there is no guarantee that you will actually have a speed up, because then it becomes a complex function of implementation, engineering, CPU, GPU sort of interactions, because part of your model is running on a CPU and so on. So that becomes less exciting in some ways, but obviously that's a better way to go about. Instability is still a problem there. In fact, understanding instability in hybrid models is still an open problem in that sense. So because now you basically have a system that still looks like this, except part of it is a numerical solver, so the discretized system on a low resolution, part of it is a neural network. So you have an ML model and a numerical solver interacting with each other. So stability is still a concern, and the way people work on those systems still now is that they try a bunch of different things and hope that it's stable. I think we have more understanding of stability in a fully AI based emulator than a hybrid model. So yeah.
Okay. Okay. Yeah, I just have one other question from my end is so currently when you are studying these kind of systems, uh, are there any underlying manifold? And if for certain systems there are some known underlying manifolds, can we leverage it in some way? This is probably not directly relevant to what you're
No, it is. It is.
talking
It's,
about.
I think it's a very interesting question. It really is. So I'm sure there is an underlying manifold, because, well, let's forget about weather and climate for a second. If we're doing PDEs, like reasonable PDEs that may not be like super high Reynolds number, there is you do get reduced order models that are fairly useful, right? So there is an underlying manifold in many systems. There is an underlying low dimensional manifold on which, if you evolve the system, you would get sort of stable statistics, and you can go back to the original space. And that's something that we've been like thinking about, and it's a separate discussion we've been thinking about for a while now. Estimating this manifold for multi-physics systems is usually hard. So the typical way to do this is like fit an autoencoder, right, and get a
Mhm.
latent space, and then I want to evolve in the latent space, and I think that's the right approach to do it. Except when you're evolving that latent space, there is a chance that maybe you got to the right manifold with your autoencoder, but then when you train the model and you're emulating the model in that latent space, the emulation goes off that manifold. There's no way to guarantee that that emulation would be stable in that manifold either. So the stability problem is still there, except now it's in that reduced dimensional space. How do I ensure that no matter how I'm evolving the model, I still remain in that manifold? And there's an interesting way to address it, and that's something that we've been doing right now. It's basically using the same logic that language modeling people do, is that don't frame your problem as a real valued problem. Don't predict the state in real space. Predict the state as a high dimensional class. So you can think of it, if your system lies between -5 and 5, how about we divide -5 and 5 into 10,000 small strips, and instead of predicting the actual value of x, we predict which of these strips it would belong to. That way you are always constraining this model to remain on one of these strips, which arguably makes up your manifold.
Mhm.
uh, of course, there's a challenge. There are other challenges with that, but there's some advantages to doing that as well, which is you kind of get the same. You can use the same innovation that you have in language models and scale this up to like bonkers dimensions. So yeah, I think that's the way to go about it. Finding this manifold is hard. Even when if you do find that manifold, or maybe there's more than one manifold that you can project onto, keeping it on that manifold during time integration boils down to the same problem.
So you would have a band, like in a Gaussian process regression, you have a band across the. Okay, okay, okay,
Yeah.
okay. Yeah, that's very cool. Okay, thank you so much. And if anybody ha does anybody have any other questions? If not, then we will thank the speaker and thank for your time, Ashish, and staying up so late. And
Thank you
great
so
talk.
much. Thank you. Thank you so much.
Thank you. Okay. Bye, everyone.
Bye.
Bye.
Bye, Antarik. Bye.